Okay, today we're going to look at how we can design circuits entirely using Nand gates. But before we get into Nand gates, we're going to do a quick recap of what AOI logic is. AOI logic, as we have said in the past, AOI stands for AND, OR, and inverters. Inverters are also commonly known as NOT gates. And by now, all of us should know that the truth table for an AND gate is one only when both inputs are a 1. For every other combination of inputs, we're going to get an output of 0. And for the OR gate, the only time we get a 0 is when both inputs are a 0. All other combinations of inputs will provide you with a 1. For the inverter, when we provide a 0, it simply gets inverted to a 1, and when we provide a 1, it gets inverted to a 0. Having said that, now we're going to quickly look at the NAND gate, which, as its name implies, it's an AND gate coupled with an inverter. And we use the shortcut of this to symbolize the NAND gate. So these two are equivalent. So the NAND gate, as its truth table, has exactly the opposite of the AND gate. So if the AND gate has inputs of X and Y, then the output of an AND gate for the following truth table is going to be 0, 0, 0, and 1 only when both inputs are 1. So that is the truth table for the AND gate. And then if we look at the NAND gate should be exactly the opposite because it gets inverted. So here's the input for the here's the truth table for the AND and the NAND gates. The NOR gate, again, as the name implies, is a NAND and a NOT and an OR. So we have our OR gate here, followed by the inverter, and again, the shortcut for it is simply a bubble. And so if we were to look at the truth table for this, it would look something like this. So here's the OR, and here's the NOR, 0, 0, 0, 1, 1, 0, 1, 1, and as we said earlier, for the OR, we only get a 0 when both inputs are 0. So that means the only time we get a 0 is there, everything else is a 1. And of course the NOR will be the exact opposite because it gets inverted right there. So those are the truth tables for the NAND and the NOR, as well as the AND and the OR and the inverter. So the focus of this lesson, however, is not to learn the truth tables, but to utilize NAND-only gates where there exists AND, OR, and inverters. So what we're going to do next is we are going to wire NAND gates in such a way that they will behave exactly like AND gates, OR gates, and inverters. As you can see, the NAND gate and the AND gate, the NAND and the AND gate are almost identical, with the exception of that inverter. So if we want to, we can work with this first, but we are going to start with the inverter because we're going to need it for the remainder of the examples. So what do we do first? Well, as I said, the first one that we're going to work with is the inverter, which, if we consider the input X and the output F1, when we get a 0, we should get an output of 1. When we input a 1, we should get an output of 0. So if we then draw our NAND gate, the way we make it behave like an inverter is by joining the two inputs together. So when you provide x here, you should get an output of F2. So we have a new x and a new output, which is F2. So if we provide this with a 0, both inputs are 0. And since this is a NAND gate, not an AND gate, the NAND gate produces a 1. And when we provide it with an input of 1, both of these are 1. 1 NAND 1 is a 0. So this behaves exactly the same way as the inverter. So we say that these two items in the clouds here are what we call gate equivalent. These gates are equivalent. They're not the same. They're not identical. They produce the same results. Therefore, they are equivalent. So that is the inverter. The next gate that we're going to look at is the AND gate. The AND gate, as we saw earlier, behaves in the following fashion. We have inputs x and y. We will call this F3. So for the following combinations, F3 is only 1 when and if both items are 1. So this will be 0, 0, 0, 1. So how do we make this behave? How do we make the NAND gate behave this way? Since this is already a relative of the AND gate that has a NAND at the end of it, when we put another inverter at the end, we reverse the damage done by this AND, and therefore this is an AND gate. And we can prove that by running the table. 0, 0, 0 NAND 0 produces a 1, which then inverted produces a 0. 0, 1 produces a 1, which then inverted produces a 0. 1, 0 produces a 1, which then inverted produces a 0, and 1, 1 produces a 0, which then inverted produces a 1. So this truth table, if we call this F4, produce 0, 0, 0, 0, 0, 0, 1. Therefore, F3 and F4 are equivalent. Therefore, we can say that this is an AND gate. We have a slight problem, however. We cannot use this gate. We have to use NAND gates only. And we have proven earlier that this little guy here is equivalent to that little guy there. So we can simply replace that guy with this NAND gate. And it will look something like this. So we say then that this and this are gate equivalent. So far we have replaced an inverter with its NAND gate equivalent, and we had replaced the AND gate with its NAND gate equivalent. The last one we have is the OR gate, which is a little bit more complex. Nevertheless, it requires the same knowledge and skills that we've used before. So remember that the truth table for this gate, and I guess we're up to F5. The truth table for this gate, given inputs of X and Y, is always 1, with the exception of when both inputs are a 0. So how do we do that with an inverter? Well, as I said before, this requires a little bit more complexity than the previous one. We simply invert both inputs before producing them to a NAND gate. And if we take an input of 0, 0, 0 inverted becomes a 1, 1, 1, NAND 1 produces a 0. So we label this F6, we have a 0, which matches so far. Then we produce 0, 1, 0, 1, and a combination of 0, 1 will produce down here a 1, 0. 1 NAND 0 will produce a 1. So far, so good. And then we're going to go to 1, 0, 1, 0, will produce 0, 1, 0, 1 produces a 1. So far, so good. And then we go to the last one, which is 1, 1, which produces 0, 0, 0, NAND 0, again produces a 1. So we are right on the money. So we can then say that this circuit is gate equivalent to that circuit. So anywhere we have an OR gate, we can replace it with this cloud. Anywhere we have an AND gate, we can replace it with that cloud. And anywhere we have an inverter, we can replace it with that cloud. So let's look at an example of how this is done. So the example that we're going to use is providing A, B, let's invert it, and C going into an OR gate. And then all of this going into an AND gate. So we happen to know that, make them a little darker so that it's easier to see. So we happen to know how to replace this little item right there. So that is the first thing we should do. B gets replaced with an inverter that we specified earlier. Done. Then this guy, let's change this up a little bit. Let's make that an AND gate. And let's make this an OR gate, because we're going to have some interesting things happen if we make this an AND gate and we make this an OR gate. So C and B inverted, because remember, this is B, but when it came through here, it got inverted. So C and B inverted go into an AND gate. And the AND gate, we said earlier, is this guy followed by an inverter. Right? So we replace that cloud with this stuff, which is its gate equivalent. So that cloud and that guy are gate equivalents. Now we need to replace the OR, which feeds from A. And remember, the OR has two inversions at the beginning, and they feed into an AND gate. So having done that, a couple of things that we want to take a closer look at. First of all, we have a couple of interesting situations happening here. We have two inverters back to back. And you might notice that we have three inverters, but we have two that are back to back. For those of you that caught this, you may notice that this situation here is not necessary, because if we say that the output at this point is W, when we come out here the output is W inverted. This W inverted gets inverted once more, therefore this becomes W inverted twice at this point. And we know that W inverted twice is exactly the same as W. Therefore, what that means is that we could simply run a wire from this point to this point, bypassing all of this. Therefore, the two inverters cancel each other out. This one is not back to back, so you cannot use that logic here. If we had another inverter here on this line behind this one, then we could use the same logic. But there's nothing back to back. There is no inverter back to back with this one for us to be able to do this. So having said that, now we end up with a slightly simpler form of the circuit as a result of these simplifications or these cancellations that we did there. So we are going to have, again, A, B, and C. B still gets inverted once, feeds into a Nand gate that feeds over here. And then A still has an inverter. That inverter is right here, and they all feed into this guy right there. So we took a circuit that had 1, 2, 3, 4, 5, 6 logic gates and reduced it to 4 logic gates. So 33% roughly savings. In the world of computers today and telephones where billions and billions are made all the time, 33% savings is pretty good. Furthermore, this circuit makes it for a small component, 33% smaller. And of course, there would be some kind of electrical delay happening because of these two additional circuits. When you consider that there are millions of gates in your computers and your telephones, that is a considerable savings. We will have a quiz next week or this week, depending on when you're looking at this video. If you're looking at it over the weekend or Monday, we are having a quiz coming up. I expect to see all the work, like I have shown, with the clouds identified, the cancellations, what replaced what, etc., etc., etc. You need to fully understand what you're doing. So be ready to show all your work in the quiz for full credit.